All right, next I want to talk about one really important application of Faraday's law, and that is a transformer. All right, so let's draw what a transformer is first and then analyze what happens. So let's say we have a piece of iron that is shaped like a square donut, okay? So we have a piece of iron that is shaped like this with a hole in the middle. Okay, square donut. Now you see what I mean. It looked squarer from this side. Okay, so let's say that I take some wire and I wrap that wire around this side a bunch of times. So I have some wires over here that are just wrapped around this side and then come off over there. And let's say I have another wire that does the same thing over on this side. Okay, so one property of iron and other ferromagnetic materials is that they trap magnetic field lines. So if you have a magnetic field, like, let's say, just really quickly, we have a magnetic field from a bar magnet that at this end looks kind of like this. If I have a piece of iron near this, these magnetic field lines are all going to want to go into the iron and kind of get trapped in there, kind of like that. So the iron kind of attracts these magnetic field lines to it. Okay, so the reason that's relevant here is each of these coils of wire, if we put a current through them, they are going to make magnetic field, and that magnetic field, those magnetic field lines, are going to be trapped in the iron. Let's do this in another color. They're going to be trapped in the iron, and they are going to go through the other coil. So this iron core is, we would say, coupling the magnetic fields or the magnetic flux in these two coils. So let's talk some specifics here. So on the left side, if I have this coil connected to a oscillating source, and I guess there should probably be some resistance here if we're hooking up a voltage source. So an oscillating voltage source we have not seen yet. We will be spending more time with it later in the class, but we draw them like this with a little sine wave in there. So this is making a voltage, just like we saw in the last lecture. Sometimes it's positive, sometimes it's negative. It's oscillating like a sine wave. So that's V as a function of t. Okay, and over here, let's say we are measuring the voltage that we get on our loop over there. Okay, so this core, like I said, it's coupling the flux of the two coils. This means that that the flux going through this coil is going to be equal to the flux going through this coil. So if we label these sides, I'm going to call this side 1 and side 2, we have that the flux through side 1 is equal to the flux through side 2. And the flux we get depends on the number of turns we have around this. So remember, in the last lecture, when we had a coil of wire, Faraday's law gave us this extra factor of n, right? So if I have n windings of the coil on the left, I should say n1, I guess. N1 turns around there, and N2 turns on side number 2. Now remember, from Faraday's law, we know that for coils of wire, our EMF is equal to N times d flux dt. So, I would like to know what voltage I get on side number 2. So if I take the time derivative of both sides of this, if these two fluxes are the same, then d phi 1 dt equals d phi 2 dt, and each of those is equal to the voltage over N, the number of coils. So d phi 1 dt is equal to, we'll go over to the left here, EMF 1 over N1, which equals EMF 2 over N2. Okay, so lastly, we'll go over here. If I want to solve for E2, and now we can call these EMFs or we can call them voltages. We'll switch to the voltages now. So voltage 2, solving here, is equal to voltage 1 times N2 over N1. So over here, we get a voltage that is related to the voltage over here by this factor of the ratio of the number of windings on the two sides. So in other words, if we have a few windings over here and a bunch of windings over here, so N2 is much bigger than N1, we get a coefficient here that is much bigger than 1. Like you could have 100 times as many windings, and so you get a factor of 100. You can get 100 times the voltage on side 2 than you do on side number 1. So that's kind of crazy. You can use this very simple device. I mean, we could all build one of these very easily, and radically change the voltage you get. So this is how you can easily change oscillating voltages from low voltages to high voltages. So this is important. This is how we can have a power grid that uses high voltage for distribution, which is more efficient, but very unsafe. And then you can use a transformer to change that voltage to a lower voltage before it gets in your house. So a little language here. So this side of the transformer is called the primary. This side is called the secondary. So the primary side is the input side. The secondary side is the output side. And you can make transformers that are step up transformers where N2 is greater than N1. So V2 is greater than V1, or step down transformers where N2 is less than N1. There are also special applications for isolation transformers where N1 equals N2, and you're just using the transformer as kind of a filter to separate one side, your input side, from the other side. All right, the last thing I want to talk about with Faraday's Law is a couple other kind of oddball applications. You'll learn more about transformers in Physics 315 electronics if you take it. Two other things about Faraday's Law. So if we have a piece of conductor, so now let's imagine we just have a slab of some conducting material, and we have some magnetic field here. Maybe it's a solenoid that's, making a magnetic field when it has a current going through it or something like that. So this is making some B field that goes through our conductor. Now, if our B field changes, we can imagine some little loop of our conductor is going to behave just the same as a wire in that place, right? A conductor is the same as a wire, it's just that we have more conductor there too. So if this magnetic field changes, we are going to induce a current just in this block of conductor. So this is called an eddy current. Just like an eddy in a river. And so yeah, you can induce these eddy currents to flow in a conductor. There are lots of cool demos of eddy current damping behavior, which I will send out and you guys can see. Lots of really cool magnet stuff. So this isn't, this doesn't have to be a solenoid. This could be a permanent magnet, and it doesn't have to be turning on or off. You could also have something like, here is our conductor. Here is a permanent magnet that is moving with some velocity, and so it's making this magnetic field that is like, if you're a point sitting here, you're like, this magnetic field is going past you. You're kind of feeling this magnetic field turn on and off. That's going to give you a d phi dt. That's going to give you some, some eddy current going around that point. So useful for like magnetic braking. And also, this is how metal detectors work. So metal detectors work by having basically one solenoid over here making a magnetic field that is oscillating back and forth. So this is making some big magnetic field. That magnetic field is changing pretty rapidly back and forth. And over here, you have some coil that you are just measuring the voltage of. And if this thing is oscillating at some rate and it's some fixed distance away, you're going to measure some voltage over here, but you know exactly how big that is. You know exactly what to expect. If there's a piece of metal in here, copper or whatever, this oscillating magnetic field is going to induce eddy currents in that copper. You're going to get currents flowing in that copper. Those currents are going to make their own magnetic field, right? Lenz's law, they're going to oppose this change in magnetic field. So this thing's going to make its own little magnetic field because of the current, right? You have this little current flowing in there that's going to generate a magnetic field, and that is going to change what you're measuring in this current, in this coil, right? This is changing or potentially changing the flux in this coil. So in this way, you can tell if there are metal objects, they don't have to be magnetic objects, they just have to conduct well enough to get these kinds of eddy currents flowing in them.